Welcome to the PLC Professor's Workshop and Lab. This is where we sort out all of our lab projects. This particular lab project, M20, is an extremely short lab project. I even considered just not even doing a talk on it, but we'll talk about it anyway. So M20 requires you to recall or to go find one of the last projects you did in part one, semester one. And it was a project that you had some conveyors and it had a loop system and I had you take the logic that was in the sequence file and split it up into different pieces. In other words, it was more about organizing your logic for ease of troubleshooting than anything else. Meaning that when you got done, what you had in sequence would be just the logic that runs the conveyors, not the lube logic. So the lube logic was moved into a separate program file called lubrication. And it's a conceptual lab project. As a matter of fact, if you have part two, semester two of the manual, but you don't have part one, then you don't even have that logic. So what I did was I advised you to just kind of read through it to see what we were doing and then not actually try to do it with your simulator or your hardware. The next lab project was M21, and that was back to the conveyor system and then using counter instructions. So let's look at both M20 and M21. In our sequence, we had the lubrication logic using the retentive on delay timer, the timing pulse, and our lube solenoid and lube complete logic in parallel with the motor conveyor coil. In other words, this coil right here controlled the motor conveyor for conveyor 1, conveyor 2, and conveyor 3. And basically what we did is we split out the lubrication logic. That's real simple. Just select that rung, Control C, Control V. Now you got two rungs just alike. So on this one, actually we'll do this one. We deleted that logic. Then up here we're going to delete the motor conveyor and we're going to delete all of this logic. And what that leaves us, we need to add in a instruction that looks at motor conveyor 1, because remember that this logic right here, the RTO, the TP, and this coil and this pulse falling or one-shotted coil was in parallel with motor conveyor 1. Therefore, if this bit was turned on, then this logic was enabled. So we just put an instruction here. Now this logic, we're now going to Control C to copy it, go to lubrication, Control V, delete the unneeded rung. You don't have to. This isn't like RS Logics. You could leave in a shorted rung. Then we go back to sequence and we remove this rung. So we delete it. Now you see we have system, logic, motor 1, motor 2, and motor 3. And of course, we could move any other logic that we have, like we could move the fault logic. We could move that into another program called faults. I only had one loop system and it was on conveyor 1. You would duplicate that for conveyor 2 and 3 if you're going to put loop systems on those conveyors. Also, I noticed that I want the lubrication right after sequence. So buffer inputs, sequence, lubrication, buffer outputs. Now remember that these push buttons, this logic was there to simulate these push buttons. If you're using the simulator, you would be using real I/O memory locations. But remember, this was just a 2-page lab about stripping certain functions out of sequence rungs and putting them in their own program. That way, when we look here, and if a motor is not running, it's real simple to see what's involved. Whereas before, if we had all the lubrication code in there, someone that wasn't familiar with logic would have to kind of sort through that. So that's it for M20. This is our application, and we are using the count up, count down instruction to count cartons on to conveyor 1 and off of conveyor 1 onto conveyor 2. Now we don't have a counter to count them onto 2 conveyor, just one counter, one count up down that counts them on with 1 photo eye and counts them off with 3 PE. So we start out with 1 PE not blocked, in other words, nothing in the optical path of 1 PE. Our counter data type has a process variable of 3 because we're saying that you can't have any more than 3 on the conveyor. We can't fit any more than 3 on there. And right now our control variable is 0, meaning none counted on. So I don't have these cartons moving in our illustration here. But when the carton rolls down the gravity roller conveyor, hits the leading edge of conveyor 1, conveyor 1, if it's energized, pulls it on and breaks photo eye 1, and now we up count. So when the rung in condition for the CU control variable goes from false to true, it increments up 1. And then as the carton passes on through photo eye 1, so you can see in the image to the left that first carton has left photo eye 1 and a second carton has now broken the beam for photo eye 1. It's in the optical path. And on that false to true transition, it counts up to 2. And then when the photo eye clears, it remains 2. So there is a little space in between the cartons. And that can be accomplished in many ways. We're not dealing with that in this particular lab project. And then when the third carton breaks photo eye 1 PE, then the CV goes up to 3. And when it clears photo eye 1, it remains 3. Now we have 3 cartons on the conveyor, and we are going to move the first carton into photo eye 3. And when we do that, you see photo eye 1 still false. In other words, it's off. Count up is not true, but look at input 4. Input 4 is photo eye 3. Notice that it says true, whereas in the previous illustrations it said false. So it seems a little odd maybe to you that we have some logic, if you like, feeding into the CU control variable, but not into the CD variable. We just have a field there, and we have a memory location IN04, which we know is photo eye 3. And when that first carton breaks the optical path of photo eye 3, then this count up down counter counts down once. And when that carton clears photo eye 3, the input 4 goes back to false. But it's the false to true transition that causes it to count up or count down. And then when the second carton enters photo eye 3 optical path, it counts down again. And when it clears, it remains at that counted down value of 1. When the last carton breaks the optical path for photo eye 3, then we have counted down to 0. The problem with this approach that I see the problem, and what we're trying to do here is take you beyond what you might do when you initially start programming, where when it breaks the photo eye, you say, hey, I've got a carton. And when it breaks the exit photo eye, hey, one's leaving. Well, If we went all the way back and look at the first illustration, when the carton broke photo I1, it wasn't really on the conveyor. You're just assuming it's going to continue moving until it's all the way on. And when you look at the bottom illustration here, you can see that that third carton, even though it's been counted down and off of the conveyor, is still sitting all the way on the conveyor, because we executed the count up when 1 PE saw a carton and counted it down when 3 PE saw a carton. That's not the best application. So we had you make some improvements to your logic. And now, instead of doing anything when it sees the leading edge, I'll back up here. This all takes place when the optical path is broken by the leading edge. In other words, when input 2 or input 4 went from false to true. Here we're taking the trailing edge. In other words, we're not going to do anything until the carton leaves the photo eye. Reaching the photo eye isn't going to do anything, but when it leaves, then the rung goes true. Now you could put these two rungs in any order that you want. If I don't explain where to get the manuals and what they are in the videos, then I get dozens of emails asking where to get the manuals. This RS Logix 500 manual is really the culmination of quite a few years of MicroStarter Lite, MicroStarter, and RS Logix 500. RS Logix 500 will program all SLC 500s and all MicroLogix. MicroStarter and MicroStarter Lite will only program MicroLogix. The starter is not free. It's about $200. Starter Lite is free, but Starter Lite will only program the MicroLogix 1000 and 1100. Then for 5000, RS Logix 5000, Studio 5000, we have 3 volumes, Fundamental Programming, Programming Examples, which is really one manual broken into 2 volumes, and then the Advanced Discussions and Lab Projects. The software for this hardware that this programs, the least expensive license is about $1,000, just under $1,000. And the hardware is also relatively expensive. You can find used compact Logix with some I/O for in the $500 range, but the minimum license is going to be just under $1,000. For Connected Components Workbench with the Micro 800, the software is free. So you don't have to buy any hardware. Starting with version 12 of CCW, they included a simulator that works really well. And we really emphasize the simulator in all of our manuals. We also have a separate volume for PanelView 800 and PowerFlex 525. The PanelView 800 projects in this third volume, they are integrated into the actual lab projects in Part 1 and Part 2. So after you do a lab project in Part 1 or Part 2, for the most part, most of the labs, you can then immediately go to the third volume and do a panel view lab that integrates with the project you did in Part 1 and or Part 2. Not all the projects in Part 1 and 2 have PanelView 800 projects that complement them. And then for PowerFlex 525, we have both projects using controllers, and also we show you how to hardwire your PowerFlex 525s with push buttons and lights. For the volumes that you see, the lecture discussions are complete and available for all but the Part 2 of the CCW manual. Most of them are complete and currently going on YouTube free, and we don't have any done yet for the third volume for the PanelView 800 or PowerFlex 525. But keep in mind, you don't need to subscribe to the videos to do the projects in these manuals. The videos are for people that would like a little bit more explanation and tutoring. Have a nice day.